Welcome to today's paper reading. Today's paper is titled, Strengthening Multimodal Large Language Model with Bootstrapped Preference Optimization. This paper was published on AR14 by Renjie PI and colleagues from the Hong Kong University of Science and Technology. The abstract highlights a significant issue with multimodal large language models, MLLMs, which is their tendency to generate responses biased towards their pretraining corpus, thereby undermining the importance of visual inputs. This bias is conceptualized as a preference for pretraining statistics, which hampers the model's ability to ground itself in visual data. To address this, the authors propose Bootstrapped Preference Optimization (BPO), a method that involves preference learning using datasets that include negative responses generated by the model itself. This approach includes two key strategies. First, using distorted image inputs to elicit responses that exhibit the pre-training bias, and second, employing a text-based large language model to introduce erroneous but common elements into the original responses. These undesirable responses are then paired with original annotated responses to form a preference dataset, which is used to perform preference learning. The results show that this method effectively reduces the pre-trained LLM bias, leading to better grounding in visual inputs. Extensive experiments demonstrate substantial performance enhancements across various benchmarks, positioning this approach as a state-of-the-art solution in multimodal conversational systems. The emergence of large language models, LLMs, has significantly advanced the field of AI, particularly in natural language processing. These models, trained on extensive text corpora, possess a wealth of knowledge, enabling them to generate text that is both helpful and contextually appropriate. With the evolution of LLMs, multimodal large language models, MLLMs, have seen rapid improvements. These models process images using pre-trained visual encoders and integrate them with text tokens, allowing for engaging conversations with image inputs. This capability opens up various applications, such as autonomous driving and medical assistance. Despite these advancements, MLLMs face challenges, including the tendency to produce erroneous or hallucinatory responses that do not align with the input image. This issue makes them unreliable for high-stakes applications, such as autonomous driving systems or medical assistance. One major cause of this problem is the bias inherited from the LLM's pre-training stage. Figure 1 illustrates the pre-training bias during the inference of multimodal large language models, MLLMs. Due to the significant difference in data scales between text-based pre-training and multimodal alignment, MLLMs are inclined to produce responses that reflect the contents frequently encountered during their pre-training stage. This bias often overshadows the importance of visual information, leading to erroneous or hallucinatory responses that do not accurately correspond to the input image. The dominance of the pre-training distribution becomes particularly evident in scenarios where the image quality is low or insufficiently trained during the multimodal alignment phase. The development of large language models, LLMs, has seen significant advancements, particularly in multimodal large language models, MLLMs, which integrate visual data. These models have shown impressive capabilities in dialogue based on visual inputs. Alignment of these models with human intentions is crucial, achieved through methods like reinforcement learning from human feedback, RLHF, and proximal policy optimization, PPO. However, MLLMs face challenges with hallucination, where models may inaccurately represent visual data. Efforts to address this include using external tools and specialized training techniques, though these come with their own limitations. Figure 2 showcases several examples of responses generated by a multimodal large language model, MLLM, before and after the application of Bootstrapped Preference Optimization, BPO. The responses post-BPO demonstrate a significant improvement in grounding on visual inputs, leading to more faithful and less erroneous outputs. This enhancement is crucial for the reliability and practicality of MLLMs in real-world applications, particularly those requiring high-stakes decision-making. Figure 3 illustrates the generation pipeline for negative responses. At the top, image weaken prompting is shown, where noises are injected into the image features to elicit responses containing pre-training bias. This method aims to highlight the biases present in the model's training data. At the bottom, LLM bias injection is depicted, which involves explicitly modifying the details of the ground truth responses by injecting erroneous but common elements. This approach is designed to simulate common mistakes or biases that the model might make, providing a controlled way to study and potentially mitigate these issues. The figure effectively demonstrates two distinct strategies for generating negative responses, each with its own method of introducing bias into the model's outputs. Figure 4 illustrates the degradation of MLLM-generated responses as the level of added noise increases. As noise steps grow, the visual faithfulness of the responses significantly declines, resulting in the generation of hallucinated objects. This phenomenon highlights the over-reliance of MLLMs on knowledge learned from the pretraining corpus, which our BPO method aims to mitigate by suppressing the unwanted pretraining bias. The preference dataset D is composed of tuples containing an image I, a query Q, two responses R1 and R2, and a preference signal P. The signal P indicates whether R1 is preferred over R2, P equals 1, or vice versa, P equals 0. Manually annotating such datasets is a time-consuming and costly process, often involving crowd workers to identify and score responses. In contrast, there are numerous existing datasets for supervised fine-tuning that are annotated with high-quality image question-answer triplets, which can serve as positive responses in preference pairs. Figure 5 illustrates the impact of image weakened prompting on the output of a multimodal large language model, MLLM. As noise is progressively added to the image features, the log likelihood of the word bear begins to decline. Simultaneously, the likelihood of words like person, man, people, and woman starts to rise, eventually surpassing that of bear. This shift demonstrates how the model's pre-training bias begins to dominate over the image information when the image is weakened by noise. This phenomenon effectively highlights the potential biases inherent in the MLLM's pre-training process. Table 1 provides a detailed prompt for error injection using the LLM component of the MLLM. The prompt instructs the LLM to modify responses by changing details such as object existence, attributes, and counts, ensuring the modified responses remain logical and common in reality. The table includes several examples of original responses and their corresponding modified versions, showcasing the types of changes the LLM is expected to make. Table 2 provides an overview of the data sources used to construct our preference dataset. The dataset is uniformly sampled from popular visual instruction tuning datasets. The first source is ShareGPTV, a high-quality image captioning dataset annotated by GPT-4v, which contains detailed responses with rich visual concepts. The second source is LLVAR, a VQE dataset consisting of images with rich texts. The third source is LLVInstruct, an instruction dataset comprising of image-based conversations. These datasets collectively provide a diverse and comprehensive set of visual and textual data, essential for training models to understand and generate responses based on visual inputs. The Bradley-Terry (BT) model is a common assumption in preference learning, which posits the existence of a reward function asterisk operator, IQR, that maps to a preference probability using a sigmoid transformation. The learning objective under this model involves optimizing the expected reward while penalizing the KL divergence to stay close to the initial model. Direct Preference Optimization (DPO) simplifies this process by avoiding the need for an external reward model, instead maximizing the original objective directly through a negative log likelihood loss function. Table 3 presents the results of various models on the MMVET and LLV-WILD benchmarks, highlighting consistent performance improvements over baseline models. Notably, the tuned LLV 1.5-7b BPO model surpasses the larger LLV 1.5-13b baseline in a majority of tasks. This table underscores the effectiveness of the tuning process in enhancing the performance of the models across different tasks and benchmarks. The model was fine-tuned from checkpoints of LLV 1.5 using LoRa with a rank of 64 and a learning rate of 2 × 10⁻⁶. The training process was conducted on 8 A40 GPUs with a batch size of 4 per GPU, taking approximately 17 hours for the 7B model and 28 hours for the 13B model. For evaluation, Benchmarks such as LLVA bench and MMBet were used to assess the model's helpfulness, while Object Hall bench was used to evaluate visual truthfulness. The results show consistent performance boosts across all tasks, with the tuned LLVA 1.5-7b BPO surpassing the larger LLVA 1.5-13b baseline in most tasks, indicating significant improvements in both helpfulness and truthfulness. Figure 6 illustrates the log probabilities of responses across the training process. The left graph shows the log probabilities of positive responses during the training of our model. The middle graph presents the log probabilities for negative responses during the same training phase. On the right side, the log probabilities for ground truth responses during supervised fine-tuning, SFT, are displayed. The mean value of every interval spanning 100 steps is plotted, with standard deviation visualized by error bars. Notably, the log probability for negative responses consistently decreases during BPO, while the log probability for positive responses remains stable. Conversely, the log probability for ground truth responses steadily increases for SFT. This suggests that preference learning aims to establish a clear margin between the likelihoods of positive and negative responses, suppressing pre-training biases. In contrast, SFT aims to memorize ground truth annotations, potentially leading to overfitting and catastrophic forgetting. Figure 7 illustrates the performance improvements achieved by Bootstrapped Preference Optimization, BPO, and supervised fine-tuning, SFT, on two models, LLVA 7b and LLVA 13b. The figure clearly shows that BPO consistently delivers superior performance compared to SFT across various dataset sizes. This consistent outperformance by BPO validates the superior sample efficiency of preference learning over SFT, highlighting the effectiveness of BPO in enhancing model performance. Table 4 presents a comparison of various models against SFT baselines, constructed from positive responses in the preference dataset. The data reveals that the LLVA 1.5-7b BPO model consistently outperforms the larger LLVA 1.5-13b baseline across multiple tasks. Interestingly, the SFT models, despite being fine-tuned, show only a marginal improvement in performance compared to the baseline methods. This observation underscores the critical role of negative responses in the preference learning process, highlighting their indispensability for enhancing the helpfulness and truthfulness of the MLLM. Table 5 presents a comparative analysis of model performance using different types of responses: baseline, self-generated, and image weakened. The results indicate that while there is a slight improvement in performance with self-generated responses, the image weakened approach yields the best overall results. Specifically, the REC OCR scores are 37.0 for the baseline, 38.6 for self-generated, and 38.9 for image weakened. The total performance scores are 31.7 for the baseline, 32.4 for self-generated, and 34.3 for image weakened, demonstrating the effectiveness of the image weakened method in enhancing model performance. The paper introduces Bootstrapped Preference Optimization, BPO, as a method to reduce bias in multimodal large language models, MLLMs, when generating responses from visual inputs. By using a bootstrapping technique to curate paired preference datasets, which include negative responses generated by the model itself, BPO helps the model to ground its responses more in visual information, thereby suppressing the preference for pre-training biases. This approach results in notable performance enhancements across various benchmarks, pushing the boundaries of current multimodal conversational systems. The authors hope that this method will inspire further research into achieving stronger multimodal alignment. The paper acknowledges two main unresolved issues in the Bootstrapped Preference Optimization (BPO) technique. Firstly, the consideration of malicious inputs that could lead to harmful responses and undesired consequences is not addressed, as referenced in 2, 29, 43, 44, 53, 60, 71, 72, 75, 76. Secondly, the design of sample selection algorithms for filtering out potentially low-quality data is lacking, as noted in 18, 24, 38, 70, 81, 85. These issues are marked for future research to improve the model's performance and robustness. Thank you for watching.